below that fitness threshold. And so we set a maximum generations to allow it to evolve. And that'll be the stopping point. Another hyperparameter is the population size that we allow in the evolutionary process. So the population is the number of equations that are allowed to survive on to the next generation. So at the beginning of each generation evolution, a number of equations are created either through a mutation process or a crossover process of existing equations. And if those new equations perform better than the previous ones, then they survive, and they're among that population size number that we determine at the beginning. And then another important hyperparameter is the stack size, which is the maximum number of allowed mathematical operations in these models. So here on the right, I have a figure that represents this stack. We have all of these mathematical operations and their node numbers off to the left of 0, 1, 6, 9, 10. And they represent these mathematical operations in the tree here on the left. As we can see, the stack size was set to at least 12 or greater. However, we only use 7 of those possible mathematical operations for this model. And so that simplified stack, or the size of that simplified stack, is referred to as the complexity of the equations. This will all hopefully make a little more sense as I go over a simple example of symbolic regression. So we had data artificially generated from this very simple equation, 3 times sine of the x plus 2, sine of x plus 2, sorry, and allowed the symbolic regression software to use addition, subtraction, multiplication, division, sine, and cosine to try to model this data. We trained the symbolic regression software and told it to have an error tolerance of 1 times 10 to the negative 4, a stack size of 40. So we note that stack size is much larger in complexity than this actual very simple equation, with a population size of 100 and maximum generations 50. After training for these 50 generations, we arrive at the exact equation, 3 times sine of the x plus 2, and we can see how it fits perfectly. However, in an experimental context where this data isn't generated as artificially, we start to introduce sometimes noise or small amounts of error here and there, or also parameters that we might not consider to be important in the final model. They get introduced into the model. And so to avoid overfitting this noise, it's important for us to look at what's called a Pareto Front. So here I have the exact same equation that we had in the previous slide, 3 times sine of x plus 2. However, we've artificially added some noise, uniformly distributed noise, and given this to our symbolic regression software to try to find that equation. What we end up with is what's called a Pareto Front. So there's multiple equations that our symbolic regression software believes can fit this data. We have varying complexities here on the x-axis, and on this vertical axis we have varying fitnesses, or mean absolute error. And looking at the equations, this equation with complexity 6 essentially gets the equation. It has a few differences in the constants due to the noise that we introduced. However, it's of the form that we'd expect, and pretty close. As we move down and get a more complex equation, this fits the training data better and has a lower fitness, but doesn't have has extra terms that we might not expect to have, and are most likely fitting to the noise of that we introduced. As we go even further, we see an even more complex equation with more of these terms that start to get us further away from the equation that we were wanting initially. So here I've plotted the two equations. That complexity 6 equation, which was essentially the same equation that we wanted, is in green. Hopefully you can see that. Sorry, there's not a lot of contrast. And then the complexity 12, that final equation that I showed, is in blue. And we can see how it's a lot more jagged and is attempting to fit the noise in the model. This is an important thing to notice when we're selecting the models that we have, to not get the best fitting model in our population, but get there's kind of a trade-off between the complexity and interpretability and the fitness. And so choosing an equation that will perform well when it sees examples that it hasn't seen before. The symbolic regression software that we use is called Bingo. It's an open source NASA produced software that uses these evolutionary algorithms and symbolic regression. A nice thing about Bingo is that it uses a parallel island evolution strategy, which means that each processor that we allow the program to use is treated as a separate island that evolves separately from all of the other islands. And periodically we have migration where the equations move from one island to the other and sort of introduce more genetic diversity into those different islands to help. This helps us to converge to a result much quicker. So the overview of the workflow, now we've gone over the tools more or less that I used. First, we, with our finite element model, want to define boundary conditions so that the solid continuum element model has a similar behavior when different boundary conditions are applied, a similar behavior to that of the shell element model. We noticed that as we displaced the boundary conditions more, we got less of an agreement. And so those maximum allowable boundary conditions are then used in a sensitivity study where we range from the minimum to the maximum boundary condition displacements and find out which boundary conditions have the most effect on the finite element analysis results. Knowing which of those boundary conditions it has the most effect, we're able to define the different combinations that we will use in our two different models, our shell element model and our continuum 3D solid element model, into our solid element model, we will insert a crack using Frank 3D and grow it and calculate the stress intensity factors. This data, after being generated, is used by symbolic regression to create a model given crack geometry and the maximum principal stress. We're able to find the stress intensity factors. It's important to note that we found the mapping of the line weld stresses to maximum principal stress more difficult than for the scope of this project. And so the scope of this project just deals with this, these red arrows where we use the 3D model to use crack geometry and maximum principal stress as a way to map to stress intensity factors. And we leave for future work the use of these line weld stresses to be able to map to the maximum principal stress and direction and other parameters that I'll describe later that we include into our model. So the finite element model has this geometry. It's a C channel that's welded to a plate. The C channel has a flange that's 50.8 millimeters long and has a constant thickness of 3.048 millimeters. The plate is 254 by 203.2 millimeters with a 3.048 millimeter thickness. And the weld thickness also is 3.048 millimeters. This entire model is idealized as one solid material with no heat affected zone from the weld. So like I mentioned, the line welds had 4 different degrees of freedom, and which correspond to the 4 different stress values that you can calculate from them. Locally, on the weld, they would be parallel to these cardinal directions Z, X, and Y, and the 4th one being a moment about this Z axis. And so to isolate those 4 different stresses of the line weld, we applied these following boundary conditions. First, we held at 0 displacement surfaces 1 and 3 in the Y direction, surfaces 5 and 50 here in the Z direction at 0 displacement, and surface 1 again in the X direction. And so to get these 4 degrees of freedom of the line weld, we loaded surfaces 6 and 60 here in the positive Z direction, surface 3 back here in the positive X direction, surfaces 4 and 40 in the positive Y direction, and surface 4 also was loaded in the negative X direction and the positive X direction to get a moment about the weld down there. So like I said, we found that there was disagreement when we had large displacement of these surfaces, especially between the nonlinear geometry element types and linear geometry elements. We preferred to use linear geometry because of the computational savings. And so a comparison was done between the displacements across the surfaces of the nonlinear geometry and the linear geometry models. And the displacement of the surfaces was lowered until the percent difference of those displacements was below 1%. So here on this X displacement of surface 3, we applied a displacement of 0.01 millimeters because that was below that 1% threshold. And here we have all of the applied displacement boundary conditions and their maximum allowed value that we found with a similar process. To compare the solid element model to the shell element model, we similarly compared the displacements. So here on the left, we have the 2 different models being superimposed on top of each other. So up here on the top one, we have this gray is the 3D solid continuum element model, and this colorful model is the shell element model, and the displacements have been magnified by 1,000 times. So we can see that there's some disagreement in the displacements of these 2 separate models. We found that was due to the coarse mesh of the shell element model, and when we refined the mesh repeatedly in half the mesh size until we got to about 0.4 millimeters, we got convergence and had a percent difference of less than 1% in the displacements of the 2 models, and we can visualize here that they agree a lot more. So with these maximum allowed displacement boundary conditions, we performed a sensitivity analysis to understand how the boundary conditions affected the maximum principal stress at the point on the weld surface, at the center of the weld surface. We used a pseudo-random Saltelli sampling method of all the boundary conditions. Here on the right, we have the distribution. We can visualize the distribution of these displacements with the horizontal axes being the normalized displacements of each of the surfaces that we were displacing, we can see that it's more or less random and equally distributed throughout the space. We had 100 different boundary condition combinations, and the quantity of interest that we wanted to calculate was the maximum principal stress here at that red point at the center of the weld surface. We found, using the boundary conditions that contributed most to the maximum principal stress here, we were able to define 180 different boundary condition combinations, where the boundary condition that had the most effect on the maximum principal stress had the most discrete values applied to it, whereas the ones that had less effect only had a few discrete displacement values. In each of these 180 different boundary condition combinations, a crack was inserted with an initial size of 0.05 millimeters, which was decided because it would be well below the non-destructive evaluation detection ability of the crack size. So from that all the way through 80% of the thickness, we'd be able to encompass the possible cracks that we'd be able to detect and later want to predict the growth rate of those cracks. Each of the cracks was inserted perpendicular to the maximum principal stress on the weld surface, and at the point with the greatest maximum principal stress. And then, like I said, allowed to grow through 80% of the thickness at step sizes of 0.24 millimeters. We did a convergence study of sorts with smaller step sizes that didn't significantly affect the stress intensity factor calculations. And the important values that were generated in this process of analysis and crack insertion were the stress intensity factors, maximum principal stress, crack geometry, meaning the crack depth and the crack width, the initial crack orientation, and the crack growth path. I'll talk about the initial crack orientation, the crack growth path in just a second. Here's the crack growth path. We can, in this figure on the right, we can see how it started to grow downward into the plate. This was unexpected. We expected more of a self-similar crack growth. However, this was what the calculated kink angle was from Frank 3D. Given the variability of the different crack growth paths, we decided it would be important to have a feature in our model that would help us describe the crack growth path. As well as the thickness was dependent on the crack growth path, depending on how far the crack would have to travel to break through to another surface. I'll illustrate that here, where we have a simple example of horizontal crack growth, where it grows here from the left side over to the right side. The thickness was simple to calculate, just the thickness of the weld here, because the crack grows almost self-similarly. And the crack depth is the deepest point of the crack, or the closest one to that back surface. Another crack, when we rotate that previous crack 90 degrees, we start to get this crack growth path. That was also, the thickness was also defined as that thickness of the weld, and the A was the distance from the initial crack insertion point to that deepest point there. Some cracks started to grow upward, and so the thickness was taken as the point from the initial crack insertion point to where it would intersect the other surface. So this would be slightly larger than the initial, or than the weld thickness. And the A was defined as the length along the crack growth path. that that the crack front had traveled. And in downward crack growth, similarly, the thickness was from crack insertion point to where the crack would break through to the other surface, and A was that distance along the crack growth path. So after this data generation, we are able to create a symbolic regression model. And the equation that we wanted to find was for this function f, which is defined as k1, which is the stress intensity factor, divided by sigma times the square root of pi times a, where sigma is the maximum, was idealized as the maximum principal stress at the point of crack insertion, and a is the crack depth. And the equation was to be dependent on this ratio a over c, which is the crack depth over the half crack width, and a over t, which is the ratio of the crack depth over the thickness that it would grow through. These n1 and n2 values were vectors, literally normal unit vectors to two different planes. N1 was a normal unit vector to the plane of the crack face at crack insertion. So N1 was equivalent to the direction of the maximum principal stress. And N2 was a normal vector of a plane fit through all of the crack front points. That's illustrated in this figure here, where we have the initial crack kind of notated here with this white curve, had more of a horizontal insertion. And so the initial crack grew, or the initial crack had a normal vector of almost an upward normal vector. And N2 shows that as the crack grows downward, that N2 now points more to the right. So many of these models had a large enough difference between the initial crack orientation and this crack growth path that we deemed it necessary to include in our symbolic regression model. So after training, using the data generated in symbolic regression and training it in symbolic regression for 400,000 generations, we are given this Pareto Front that we similar to the one that we saw earlier. Of these equations, we tested which equations performed best on a test data set that was separated at the beginning of training, which is 20% of the data, and the training data was 80%. And the equation that fit the test data the best was this equation represented by this red dot with a complexity of 9. And that is this equation. One thing of note is that this equation was only dependent on A over C and Z2 and Y2, which are the Z and Y components of that crack growth path. We expected this to be dependent on A over T and the initial crack insertion orientation because of similar stress intensity factor equations in literature. So this was surprising to us, and we tried to find ways that we could possibly see why A over T was not included in this initial model. And one method that we saw that might help with that problem is gradient boosting. Boosting in machine learning is using an ensemble of weaker machine learning models to create a stronger one that works better when they all work better together. Gradient boosting specifically is training a new model off of the residual error of the previous model. And so we borrowed this technique in sort of an ad hoc gradient boosting way with symbolic regression, where we trained a new symbolic regression equation off of the residual error of the previous equation. This illustrates how that could possibly be beneficial. Here on the left, we have the raw data plotted with F with respect to A over T on the horizontal axis. We can see there's a lot of spread and not a lot of correlation between F and A over T. However, when we subtract that first model, F1, from F and get our residual error here, that scatter sort of collapses and we can kind of see more of a correlation with A over T. This proved useful because our equation that we trained on this residual error was then dependent on A over C and our initial crack orientation. We picked this model of the many models given us, similar to the first model, that it performed best on our test data. And when summed with our first model, it performs better at predicting. Our first model had a fitness or a mean absolute error of 0.052. And with this, we were able to get the fitness down to 0.048. And subsequently, with the third model, we were able to lower it a little bit even further. And we can show that that lowered it for both of the training data and the test data here. However, when we added a fourth model, it did not improve the overall fitness of the overall model. And so the three models was deemed to be sufficient and a convergence, and the best that we'd be able to get with this method. Something interesting from this plot is that the test error is below the training error, which normally is not the case in machine learning problems. However, this could be due to the test error having far fewer data points and thus far fewer outliers, which we'll show is what drives the amount of error. One interesting use of symbolic regression that was implemented is using symbolic regression to simplify equations. So our equation F2 here was fairly complex and difficult to interpret. And using algebraic simplification still left some components of the equation to be hard to interpret, such as like y to the y or different things like that. And so we can use symbolic regression to find a model that is essentially equivalent to this more complex model. And we are willing to deal with maybe a slight change in error with a more interpretable equation. And so this was the outputted equation from that simplification step, and didn't significantly affect the fitness of the overall model. Another illustration of how the gradient boosting method helped our symbolic regression is illustrated here. Now, it's difficult to visualize the 6-dimensional space that we're working with only in 2 dimensions. So the insights that we gather from this are maybe not optimal. However, we can see here on this plot on the left that the equation for F1 has a hard time getting F values that are high. And when we include our function F2, we're able to include those values. We also can see that the percent error ranges from 0 to above 120% here on the left, and ranges from 0 to a little over 70% on the right. And we can see that with this histogram plot where the addition of F2 reduces the number of outliers in our overall model. Like I said, it's kind of difficult to visualize these multidimensional problems in 2 dimensions, and even this 3-dimensional plot that's printed on 2 dimensions. So if you'll allow me to open up another screen, I will try to illustrate what I want to here. So this plot shows F with respect to Y2 and A over C, and the colors of the points is corresponding to Z2. We can kind of see a cluster of where Z2 is high here, and then where it's low is basically everywhere else. So we created 2 different surfaces. The surfaces represent our prediction given our model. And so we can see here how the darker surface is able to predict decently well these darker points, and how the lighter points are predicted well by this lighter surface. And that is due to the model being able to bring in these other dimensions. Then we model F1 plus F2 here with respect to Y and A over T, and then the color corresponds to Z. Again, we have another dark cluster of points over here that might be hard to see, but that dark surface is able to predict those darker points rather well. And these lighter points here are predicted rather well with the surface. The surface starts getting more complex and almost appears to be overfitting, but given the simplicity of the equations, it's probably not overfitting and more of a artifact of reducing these 6-dimensional models into just 3 dimensions. So I'll go back to my PowerPoint presentation. This will let me. Okay, so those are just those other models with different colors. In conclusion, there are important implications of this work. And I'd like to illustrate that with an example from Raju and Newman, who created an equation to model the stress intensity factors of this plate, or the crack in this plate. So here's this semi-elliptical surface crack in a plate that's being loaded in tension. And they found an equation dependent on A over C and A over T through a series of multiple curve fittings. So here we have the overall polynomial that they found, and each one of these M1, M2, and M3 are other polynomials that they sequentially sort of curve fit to fit the data. And an exciting part of the results that we're able to find is that perhaps we might be able to sort of automate this process of polynomial fitting using gradient boosting with symbolic regression. We've also shown that we can get these interpretable results of how each input affects the output using symbolic regression. We were able to show how we can map the crack geometry and maximum principal stress to stress intensity factors. However, the mapping of line weld stresses to maximum principal stresses is left for future work. We've introduced a gradient boosting technique that can be used with symbolic regression to improve the overall model and be able to find more complex equations than what are, or complex equations when those are expected. We hope to use gradient boosting with symbolic regression to revisit some classical fracture mechanics stress intensity factor solutions like the one I mentioned previously, to see if we can replicate those results using symbolic regression. And left for future work as well is perhaps a simpler geometry to be able to map the line weld stresses to the stress intensity factors, to be able to, well, by reducing the variability in the overall model, given our 3D nature and allowing the cracks to kink it in many different angles. So thank you all for listening, and I'd like to acknowledge these people and entities that helped contribute to the work that I've presented. So thank you.
All right, thanks, Kevin. I guess you can see the clap icons and imagine what it would sound like if we were all in the same room. So nice job. So I'm gonna now turn it over to the general audience, so not the committee members, to start asking questions, and perhaps just start unmuting yourself and fire away, and we'll see how that goes.
I've got a question.
Yeah.
A couple actually, but we'll start simply maybe. So when you revisited your equations, let's say after or even before you started doing the gradient boosting, were you able to get any kind of physical insight out of looking at some of those equations? So kind of talking about the interpretability of it. Were there things that were interpretable in there that made sense?
There were things that made sense physically. For example, the stress intensity factors and A over C were correlated, and we kind of expected for a greater A over C to have a higher stress intensity factor at the depth of the crack. But before using the gradient boosting, we weren't able to find any equations that maybe looked familiar in like a fractional mechanics mindset. If that makes sense.
Maybe next to so you kind of pulled out that like Z2 and I think it was Y2 were the two that were pulled out first by your symbolic regression. I was wondering if you had also looked at potentially other parameterizations of the planes. So maybe instead of looking at like X, Y, Z, you looked at rotation angles of the unit normal or something like that.
Right. I did not. I just stuck with the unit normal vectors.
Okay. And last one from me is, so you had mentioned that you saw some clustering in your Z's at least that kind of like gave you different groupings. I wonder if you had clustered and maybe classified the data, do you think that you could have maybe potentially generated a couple different symbolic regression models that kind of fit different scenarios? I'm not even sure what physically those scenarios would correspond to, but I don't know. Do you think something like that would be useful?
Yeah, I definitely think that by classifying and training on like a situation where the crack grows downward, only training on those ones, one that grows horizontally and one that grows upward, maybe. I mean, I'm just throwing out different ways we could classify it. But I definitely think if we were able to separate those clusters, we'd be able to get different equations. The reason that we didn't do that for this project was we didn't want to lean too heavily on the crack growth path, because of the final application of the problem, where we want to just be able to map the line weld stresses to the stress intensity factor, it would be harder to know that crack growth path. We'd be able to perhaps figure out the direction of the maximum principal stress and thus that N1 plane. Yeah, we didn't want to have to be able to tell our prediction model what direction the crack would grow, given the final application of the project. If that makes sense.
Cool. Was that also part of this then, to predict that crack growth direction based on kind of the initial?
Right. So we ran into issues being able to fit models that worked well, mapping those line weld stresses to those directions. And so we left that for future work and deemed it outside the scope of this project.
Cool. Thanks, Kevin.
Yep.
All right, thanks, Jeff. Are there any other questions before we hang off? I know Professor Wong, I know you always have some, so can always count on you for a few questions. So if you have one, go ahead and throw it out. Or if anybody else, this is kind of your last chance here.
For me, not today. I was interrupted by my son today, so I wasn't able to focus on the content. So, but yeah, I will ask questions later on. Maybe, yeah, try to check with Kevin.
Good. Okay, fair enough.